We're good. All right, guys. Good morning. Happy Friday. So after last week's recitation on recurrent networks, we're going to look at a specific use case that's going to be targeted for our third homework. And we're going to work on specifically thinking about sequence-to-sequence loss functions and a family used in what's called connectionist temporal classification. And we're going to specifically talk about what that means, where it comes from, and how we can think about it. All right. So Jerry, do you want to start us off?
What?
Do you want to start us off?
Okay, all right. All right, let's begin. So it's possible that I could just directly go into the CTC formulation, show you the formulas, ask you to look at the paper and figure it out for yourself in the end. But then I think it's better in this recitation to explain why we even have something called CTC, and also to get a little more into the meaning of the loss functions for RNNs. So I think we may have talked about this in the previous recitation, but here's a slide talking about what kind of tasks we could use RNNs for. In general, usually we'll have some notion of time. So time can go on forever, unlike a picture that has boundaries. Although there's the length of your sequences can be variable length. You could have utterances that are longer or shorter. When you could have arbitrarily distant context information that plays a role in making your decision. So a word that comes many words ago could still affect your classification at a specific point. When you have order in your values, but not necessarily continuity. For instance, a word could come immediately after another word, but then they don't actually have to be similar words or anything, unlike pictures where the pixels usually are fairly continuous. And lastly, sometimes you would also want to use an RNN to do some kind of computation in several steps. I think in the next lecture, Bhiksha will show you an example where we do addition using an RNN. In general, for those of you who are also ECE like me, you may want to look at the digital logic analogy. It's not that important, but it's just something interesting that I found. So we can also look at the use cases of RNN from the point of view of what kind of output data we have. So sometimes we have a many-to-one architecture, so where we need to process many pieces of data and make one final classification from it. So what we do is we make our RNN take our input tokens and in the end produce a single output. This is similar to something like sentiment analysis, where you read some text and you try to decide whether it's a good review or a bad review. We could have many-to-many architectures. In the first case, we have this, what I call a streaming architecture. It's not the actual official word for it, but that's what I call it. This is where, although you have many inputs, there's many outputs where each output is corresponding to a short segment of the input. For instance, with your utterances, there could be several subphonemes. Each subphoneme only corresponds to a small part of the input. It's not the whole sequence of subphonemes depends on the whole sequence of inputs. And so what happens is while you're looking at the input, you're generating outputs on the fly. At some point, you can decide, all right, the first subphoneme has appeared. Time to move on to the next one. This is different from the more generative many-to-many architecture, where, for instance, you have to read the entire input before you can even create the first output. This is similar to a task like machine translation, where the first word of your output, translated sequence, must depend on the entire input. So although feasibly you could do it with kind of a many-to-many neural network recurrent architecture as well, typically these are done with more attention-based systems. But on principle, they are tackling the same problem in similar ways. So this is a page showing the examples. First one is sentiment analysis. Second one is speech recognition. Third one is more machine translation. But then for the first case, we only had one output, so we could just still use the same loss functions as before, like negative log likelihood. We could use L2 loss, whatever. But then if we have multiple outputs, what can we do? So here's a hypothetical conversation. Someone could say, we just find the sum of all the losses. Isn't that easy? But then like we have these variable length output sequences as well. So if you have a longer output sequence, we have a bigger loss, which is kind of strange. So maybe you want to use the mean. But then like this, even if you think about something like this, you may realize that the output sequence and the input sequence, they don't have this like one-to-one correspondence. So like how do you even like match the output to how do you match the network's outputs to like the ground truth labels if they don't have the same length? Even if they do, they might not even like be the one-to-one mapping that you would expect. So what would you do? This is kind of strange. Does anyone have an idea? Just okay, let's go to the next slide. Yes. So I guess to get into this problem, we have to say like what kinds of errors could exist in the network's outputs compared to the labels. And we need to make sure that this loss is differentiable as well, so we can actually use gradient descent with it. With all the previous losses we talked about, it's pretty clear that they're differentiable. It's either like ground truth minus output squared or negative log of ground truth output or something. And so, but then like depending on how you choose the loss function, you get very different kinds of loss errors. So like the first case is the very simple one. Like we could get a misclassification. If it's supposed to be a 1 and we output, say, like a high probability of a 5, then that means it's wrong. If it's a regression still, if the output is supposed to be 11 point something and we say it's 0.5, then it's wrong. But then for the managed menu architectures, there's different types of mistakes you can get. And there's, of course, the obvious one, which is one of the values are wrong. For instance, if the answer is supposed to be ABCD and you said it's probably ZBCD, ZBD. If you said it's ZBDC, you'd get one mistake there. If you transpose the two, then you suddenly get two mistakes, even though that's sort of just one mistake that you've made at that point. And if you're missing one of the values in the middle, then suddenly it's very hard to see, like, what is the mistake? In this case, it's supposed to be just one mistake. You've forgotten to output one of the labels. But then, like, if you match them one with each other naively, you'll get to a point where, like, you run out of outputs and you have too few labels. And it's very hard to see what is the mistake. And for the generative architectures, this is even worse because, like, it's pretty easy to create a loss function that says it must match the answer I give you exactly, or you're completely wrong. But that's like kind of like what you do if you're a really bad teacher who's holding like the curriculum in your hand, and you're saying, okay, it's not the exact steps that you use to get to the answer, therefore it's wrong. So like it could be very similar in answer and still be completely wrong. For instance, if the network says the car sat on the mat, which is kind of semantically makes no sense. If the car maybe could park on the mat, but you know. Or like the output could have like a similar meaning, but still have very bad style. For instance, if it outputted something like this, which has it doesn't follow grammatical rules, it has like it pretends that this word was two words, so on. Even though like overall it matches like the poem that I based this on, it's still stylistically and grammatically very different.
Not even that the first one had correct grammar.
Yeah. And so like the choices of loss functions that we use for the first case, for instance, cross entropy, L2, so on. So it's just the obvious ones where we kind of take a distance between the two values, kind of divergence. With the streaming version of the many inputs and many outputs, we use what we call CTC loss functions, which is what we're going to be talking about today. Although I just want to make a note about what we do for the generative ones. So like often we do things like use discriminators. So we have a neural network whose only job is to say whether your outputs look similar to your inputs or not. Or we can use kind of versions of n-grams. Has anyone heard of the BLEU score? Okay, so like if you do natural language processing, sometimes the BLEU score comes up as one of the evaluation criteria, which is basically an n-gram loss. You may have to be careful to make sure it's like differentiable as well, but there's versions of the BLEU score that can also be used for the generative version. And there's also sometimes you use kind of embeddings where you turn the entire sentence or the individual words of it into vectors. and then you compare the vectors to see how different they are. The important bit is like similar sentences or similar outputs in semantic meaning get assigned like a smaller losses. So does anyone have questions up to this point? It's kind of like the introduction. Okay. Okay.
All right, so now we're going to start moving into actually talking about the CTC. One thing to really mention about CTC is that this is a general family of loss functions, and there are a number of ways to consider constructing it. I think the way that we're going to describe is the one actually enumerated in the first paper. And later we're actually going to talk about some poor assumptions that may be made and may not make it actually suitable for your task. And we'll talk about some ways after we go through the paper's strategy to sort of remedy that and ways that you can think about changing it. And I think it's also sort of an important lesson about how not to take whatever an author did in a successful paper as like the word of an oracle. They only saw it through a certain lens, and later you're going to have to think about adapting it and figuring out what are some bad assumptions. All right. So here's the intuition that we're going to use. So now we're going to expand our. So imagine that we have a language of possible labels. So if we have only the characters A, B, and C in our language, we're going to add a new character, the blank symbol, and we're going to design the network to output a classification at each of these inputs, and then we're going to collapse. So for example, you could be going through your sequence, and if you're not changing the output, you just emit a blank. And then, so now we basically have a many-to-one relationship. You can see that these two examples, the 4 A's, 2 B's collapse to AB, and then the 4 A's, 3 blanks, and 2 B's collapse to AB. And we're going to formally define a function that does this in a bit. And then this allows us to compare the collapsed output with the ground truth label. So even if we have a variable-sized input, a variable-sized input where we can still decide to use a normal recurrent architecture where we're outputting a label at each distinct time step. But now you can have multiple input data that are different lengths that can correspond to the same ground truth sequence. Like I may say the word cat more slowly than Jerry says the word cat. But at the end, and if we're still going to output, if we're still going to do a classification at each time step, this allows us to assign a ground truth label without worrying about having to label it over time. Like no one has to sit there and say at this time step we're in A, at this time step we're in blank, this time step we're in B, and then do a normal mean squared on that. We can actually just use natural labels. All right.
Is the idea there that like if you say cat more slowly like cat, that you basically have the same phonemes multiple times in a row?
Mm-hmm.
Yeah. So like this.
So if we're emitting a label at each distinct time step, and then if you have variable lengths, you want to be able just to say, well, he said cat, or he or she said cat, and that should be your label instead of having to actually label each time step what's going on. And you can imagine how many different permutations there are given variable length inputs, especially when you have a large language. Okay. So this is before training. It's basically spitting out random characters. You collapse it. This is the ground truth. How are we going to figure out a loss function to show the divergence between these two? And then hopefully, once we train, we can get something like this. And as you can see, the collapsed version is the same as the ground truth, and your loss should be 0. Okay, so at each time step, as we just said, the network outputs a probability distribution over the possible labels and the blank symbol, so the new language. So if we randomly select a label independently, what's the probability that we get an output sequence that collapses into the ground truth sequence? So this is the negative logarithm of this probability. Because now we have many possible, what I call label sequences that can collapse into the same labeling. So instead of finding the single most likely path, we're gonna find over the outputs. Not saying that exactly right. Yeah, what am I trying to say?
You're trying to like basically find what's the probability that you get any kind of output that collapses into the one you want.
Mhm.
So you don't care exactly how it gets there. It's just it picks one that worked.
Yeah. So basically, we call those paths. So basically, the most probable sequences that collapse into a specific labeling. So this is what we just talked about before.
It's like the more formal mathematical description, the one that's shown in the paper, which doesn't really care about your intuition, but like is very rigorous.
Yeah. So we're just going to formally define it here, so it becomes, the notation's a little bit easier when we step into some more visual examples later. So as I talked about before, the original set of labels L and L prime is the set of labels with the blank label, and then we're just going to define a sequence of variable length t as L prime to the t. So we're going to call it pi, and so given our input and a labeling, where the labeling can be, the size of the labeling can be less than or equal to x. Just as we show, they can collapse, but you could also have a labeling that's the same length as your sequence, but obviously no greater. Yeah, do a question.
What if the round trip is actually longer? Some speech really quick.
That,
I think that's the assumption is that, but like
yeah.
if it is, you may have to subdivide or like put even further.
Yeah. So basically, we're just going to do a normal maximum likelihood estimate. Oh yeah.
What is n?
Well, what's n?
Which one?
Oh, that's a great question. Yeah, that's the number of samples.
But the length of the is less or.
The length is t of each.
Wait, is this T or?
So how about the first line where d is less or equal than x?
Oh, z? Yeah, so z is your labeling, x is your input.
That means the length of the labeling, or.
Yeah, so I was specifically making a distinction between the label sequence, which is equal to x. This is the size of x, so the label sequence, and then it can collapse to something of equal length or less than it, right?
When the length of z is not equal to x, how it can catch into n pairs?
So this is, we talked about collapsing, right? So like,
I think the n here means like there's a training set of like
I believe he's asking about z and x, not n, right? Are you asking about n, or n, or
n
does,
is the size of your training set.
this is the size of your training set. This is so like this means like each sample, z like x of I. That's a single training example.
So that's why I asked what is n?
Oh, okay. Yeah, no worries. But you're clear on, okay.
Why would z be conditional with x? Because I think what you're saying is what is the most likely uncompressed sequence that maps into the compressed one?
This is sort of a machine learning terminology thing where they kind of overload the conditional. So like given the input sequence and some parameterization, what's the probability of that labeling?
Like they call z basically this like random variable, and the value of that depends on x. So that's just z given x is a specific label that you had in the training set.
But aren't you interested in the opposite because you're trying to decipher, or is it, or
Sorry?
aren't you interested in the reverse problem here? How do you recover back the uncompressed?
Oh, like this is the problem specification. This is not like the solution yet.
Okay, sorry.
Oh, yeah.
So is the z collapsed or
Z is the collapse labeling.
okay?
So, but now we're going to expand out this PZ given X. So now let's just formally define this many-to-one labeling, where we go from our expanded language, and then we shrink it down. And then, as we said before, it can be less. The length can be less than or equal to the original length of the label sequence that we get out from our network. So basically, B is what we were calling before the collapsing operation. And so now the inverse of B is now a one-to-many, and we're going to get this from it, the set. So given a labeling, B inverse of Z is the set of all possible paths that collapse to Z. So if you give it cat, you take, imagine a length T label sequence. What are all the possible values of that label sequence that can collapse to Z? And that is what B inverse of, yeah.
Two examples of B collapsing in
Sorry?
two examples of
Oh, yeah, like we forgot another underscore C. Sorry.
Oh, we did?
I think we meant to have another underscore between the two C's.
Yes, we did. But, did we?
But yeah,
In the second example?
Oh, the first one. Yeah.
Oh, yeah.
I think we.
So it should be
should've
two
been
C's.
both A, B, C, C, or both A, B, C.
Yeah, correct.
And so, like, where were we?
Okay, yeah, so basically we just define B inverse. So now the probability of a given labeling is the sum of the probabilities over all the paths that could have collapsed to that labeling. And then we just substitute, and then the negative of the maximization is now a min. So now we can use gradient descent naturally here on the problem. So this is over all the samples in your training set. And then for each of those labelings, you'll need to, if you're going to do it naively, go over all the possible paths. And there are a lot. Sure.
And explain something about the why.
Mm-hmm.
See, so basically the Y shows up inside of the set. So we're saying like, given this like output label sequence, we apply B inverse to it to get the set of all the inputs that would like collapse into that output label sequence.
Yeah.
And then like that line just here just says, if we take an arbitrary element of that set and we apply B to it, we get Y back.
Sorry. So I think the one thing that you said is like collapsing into the labeling. I just want to like to avoid confusion. I'm like calling the outputs that are the same size as series the label sequence, and then they can collapse into a labeling of variable length that's less than it.
How do you count the inverse of B?
That's now a combinatorics problem, right?
Yeah.
All the possible combinations.
Like, in theory it exists. How to like actually generate all of them could be computationally expensive. So we're not actually going to generate B inverse when I show the algorithm later.
So basically, we're setting up the formal problem where you can see like the naive way to do it, but we're going to go into a more computationally feasible strategy. Okay. Yeah. So sorry. Yeah.
So is the intuition that we're generating all the possible sequences, and then we're going to look at our input and say, does it match one of these possible sequences? Is that, in theory, what we're doing?
I believe that's the greedy approach to it, like finding the most likely labeling. But I think instead we're trying to find. What do you think, Jerry?
So like, it's not the same as like using the most likely labeling and then figure out like what the edit distance is that in some differentiable way. Because like when we're computing loss, we're actually like summing over all the different paths, and like including the ones that only collapse to the correct value and seeing how probable it is. So it's not just using the most likely one. You want me to explain? Like,
Yeah, sure. Yeah. Go through it.
Okay. Oh yeah. M we're going to use very soon in the next few slides, but in this formula we're not using M.
Are you sure this is correct?
Because I just collapsed it because M is guaranteed less than N. So like I think it's O of N plus M inside, like C to the N times M plus M, but then like M is less than N, so I just turn it into C to the N times N. Does that make sense? It's something like that, yeah. But anyways, like So basically, the naive way of doing it is basically to actually enumerate through all the different paths that you could make through the output like probabilistic sequence. And then for each one, you say, I'll collapse it. And then if it's the labeling that we wanted, then we add its probability. Otherwise, we don't. And though it would be correct and like it would be a very easy function to write to like test your CTC implementation, it will be very slow because at each point we have several different like possible labels, and then we have a potentially very long input sequence. And so we might have like up to like an exponential amount of time needed to enumerate through all the paths. And it's not very good. It'll make your computer like not finish computing until the end of the universe. And so a better way of doing it is like basically this dynamic programming approach, which is for those of you who know like hidden Markov models, it might actually remind you a lot of that. But essentially, we're creating this recursive formula that depends on that creates like sub-problems, and then we depend on those to compute the value much more quickly. And so before we get into that, we're going to show some mathematical notation of what we're going to do. But first of all, like in the paper, they've inserted blank symbols in between each of the symbols in the output labeling. This helps simplify their like algorithm a little bit. And so they define this like new output labeling that has blanks everywhere, and then they create this like different value of m, which is essentially 2 times m plus 1. And basically, from this point on, whenever we talk about the output labelings, we're talking about this modified sequence. And so what we do is that we use the symbols in the output labeling to essentially to keep track of the state of this kind of system that's going through the input and generating symbols. So like imagine that instead of like probabilistically generating symbols at each point in time and summing over the paths, instead we imagine a network that's going through several different states as it's looking through the input. So like if the output labeling has an A, then we say our network is in the A state. It's trying to generate an A at this point in time. We'll be showing a picture very soon showing you what's happening. And if it's in a blank, then like it's in the blank state at this point in time. It's trying to generate a blank at this point in time. And so what the state transitions basically work like the network is allowed to skip blank states, but only if like the states that are on either side of the blank state is different. So like if we're on state C, the network is trying to generate C, and like the next symbol is a blank because that's how we generated our output labeling. We are allowed to skip the blank state only if the state that comes after that is not C. So if output labeling has C inside, and we modify it so that it becomes C blank C, then at the first C, we're not allowed to skip the blank state to enter C again. This basically enforces the network to say we must generate at least one blank in between the two Cs.
Is there any example?
Yeah, this is exactly what we're going to show in the example. This is kind of like a visual system that I generated to show how it works. So like if our output labeling is this ABCC with blanks put in everywhere, then initially we're in like the blank state, and the network is like supposedly creating blanks at this point in time. And we're allowed to like stay in the blank state, and at this point in time we generated the blank with some probability. So like we're keeping track of the probabilities of generating the necessary symbols at each point in time. So I use the colors to like represent probabilities because like numbers won't fit inside those tiny cells. But so like in this case, we're saying the network goes from this first blank state still to that blank state, and then to A, and then skipping over the blank state to go into B, and then ... it goes through the two C's, and in the end ends up over there. And then as we do this, we're supposed to be generating the symbols that are necessary. So at this point, we're trying to generate the blank, and so our path contains like the probability of generating that blank. And then we stay in that state, but then like now there's a different probability of generating the blank the second time. And then we go to the A state. The network is supposed to output an A at this point, and so it generates the A with some probability, which is it's like that gray square right over there. So the vertical axis in these graphs is showing that the first row is probabilities of A's, second row is probability of B's, third row is probability of C's, last one is probability of blanks. The horizontal axis is time. And yeah?
What is it? Process two blanks at the beginning?
basically it's allowed to create as many blanks as it wants. This is just an example path. Like, it's also possible that it'll just go directly to A at the second step, or even from A directly into B, as we did from time steps 3 and 4. This is just like an example. And so like we can find, like, knowing kind of exactly what states the network is at each point tells us the probability of it generating the necessary sequence.
What
Yeah.
is the second line stand for?
The one with the colors?
The one have the yellow.
Oh,
This
yeah.
one? This is your actual ground truth labeling with the blanks added.
Yeah, so like we're using the ground truth labeling as like the set of states that the network goes through, although it's allowed to skip some.
What's an example path mean?
This is basically we're keeping track of the probabilities of generating the symbols as we're going through it. So like the network is in the blank state, it has like some probability of generating the blank at that point.
So we discussed before, like, that you need to calculate the probabilities of all the possible paths that collapse to the ground truth label sequence. So this is a single example of a path that collapses to it. And we're just setting up a way to think about this, and then we're going to use routing to make it more efficient.
Yeah.
And for, when you move from current time 1 to current time 2, the reason you got next blank was because the blank was more probable. I'm assuming the darker color
Yeah, you can assume that, but like, are you saying that the reason it stayed in the blank is because it's higher probability?
Yeah.
So that's not quite right. So there's no, like, in the end, we're going to like enumerate through all the different ways of going through these, like going through all the states appropriately.
It's just that we're not trying to be entirely greedy and just go for the most probable path.
And so like it's not staying in the blank state because it's a higher probability. It's just staying in the blank state because at this point in time we're assuming, like we're pretending that it goes through the sequences in exactly this order. And at a different point we assume a different like order of states. Yeah?
So if you're not being greedy, are you looking at it as like an information gain kind of a thing?
As an information gain sort of thing?
Right.
Like-
So if you had a greedy algorithm, you just pick whatever state is most likely. But if you're looking at information gain, you're looking at how pure your probability distribution is, right? So if you have a very peaky response at a blank, you're going to say, okay, it's very likely to be a blank and not likely to be anything else. So I get a lot of information by choosing a blank. Whereas if I had a uniform distribution across all of my states, I would just stay where I am because I don't have any more information by picking the maximum, because the maximum might be whatever, n over 1 over n.
So like, at least in this computation, we're not using the probabilities to choose what states to go through. In the end, the way the network can like change its probabilities based on what it's seen can actually use like some pretty smart methods to figure out whether it should be staying in the blank it should be staying with a high probability of a blank at this point or what. Yeah.
So if we're not using the probabilities to choose, what are the probabilities doing here?
So the probabilities are to help keep track of like the sum of the probabilities of each path. So this is just an example path, and we're showing like how we could think of it as going through the states of the outputs. And then like the probability of that path would be the product of all the probabilities for each symbol that we've gone through during the path.
It's sort of assuming that those events are independent.
Yeah, so like that's part of the assumption that the outputs are independent of each other.
It's not a great
Yeah. But then like the dependencies are already kept track of, like the recurrent neural network the job of that is to keep track of dependencies. And then it outputs the probabilities so that you can use them independently. Okay, so we're going to come up with these two expressions. One we call the alpha t of s, and the other we call the beta of t of s. So for now we can ignore beta. It's like alpha is a little more intuitive to think about. So it's a bit of a mouthful to say what it says, like what it means. I call it the sum of the probabilities of all the forward paths from time 1 to t that have transitioned from states 1 to s. So like s is this number that's less than or equal to the maximum number of states in the modified labeling. And then t is like a point in time. and we're saying we have paths that stop at time t, and then we have paths that stop at time t and have gotten to state S. But then we have to find the sum of the probabilities of all the paths that satisfy those two criteria. So like, the final problem would be like we transition through all the states, and then we have to go through all the time steps. So we basically have t and s being the maximum values. But then to calculate that, we can use smaller values of t and s and consider shorter paths. Yeah?
Can I go back to the last slide? So you can map the math probabilities, the example.
Okay.
Oh, so basically, if you go for like sometime, say like time 4, and then you pick any one of those states, imagine starting at the
Time 4 or time
any time. Just pick an arbitrary time. You can imagine the sum of the probabilities of transitioning from each time step to a different state that's possible.
So like, for example, this one, we can say like alpha sub 3, 3 being the t, of 2, 2 being like, since we're in the second state.
Would you write on the 4?
Okay, so, but then, how about the string?
The only thing is, it's kind of hard to show for the.
Hey, Raja, do you want to like type it into?
Yeah, I'll type it into. What do you want me to type it?
Wait, but is there a marker? Even? Okay. All right, so math. Can everyone see here? Or it's kind of hard, right? Okay, but then that could also work.
Say for the stream that I'm going to use show my mouse on the.
Okay, cool. So basically, let's consider the current time colon 3 box. So we have alpha sub 3 of 2. We have 3 since we're on like time step number 3, and we have 2 since we're on like the second state in the entire sequence. Is going to be equal to the sum of all the different paths that end at time 3 and also are on to state 2. And an example we have over here is one that generated underscore a, but there could be potentially multiple ways to get there to like end up on time number 3 and be in state number 2. The one we shown there is just an example. In this case, I think that is the only one path, but in principle, you could imagine that there's several, and we have to sum the probabilities of each. Yeah?
Underscore AA.
Let's see. So we only have to end on underscore AA. Oh yeah, so we only have to end on state A. So actually, we could have been doing AAA, because like we may have started in state 2 and stayed there forever. We're going to be showing you that like where we start in soon, like the base cases. We could have gone through underscore and then be in A twice, or we could have underscore AA, so on, as long as we ended in the state where we're generating the A's and we're on time step number 3. Good catch. I actually forgot about that. And so does that make sense for at least what A sub 3 of 2 is? We're going to be going through a lot of examples of like specific values of A. And so like, actually, does anyone have questions up to this point? Here we're going to some examples now. Okay.
So is it just state probability or is there transition probability?
Huh? Is there just a state?
Transition probability here?
The transitions over here, we're not actually like having stochastic transitions. We're like essentially going to consider all the different transitions. Yeah.
Being the next state's independent.
Yeah. So it's not exactly the same as a hidden Markov model, but it's like we can compute them in similar ways. And so like in this example, we're going to say, given the rules we have about transitioning through states, like we cannot skip through the states unless we can only skip through the blank state and only if the two symbols on either side are different. Then like we have these values, which is alpha sub 1 of 1 is just the probability of generating the 1 at time step number 1 and generating the blank at time step number 1. And alpha sub 1 of 2 means that if we're at state 2 at time 1, then we started on A, so we have to have generated the A at that point in time. And something like we have another base case, which is that for everything else, like alpha sub 1 of anything more than 2, we have 0 probabilities because no paths will actually follow the rules that we set out. Because if we have, like, if we're in the third state or beyond, that means we must have skipped the first A, and that's not possible. So there's no paths that satisfy the criteria. Sum of no paths is 0 probability. Anyone? Is that clear? Okay. So these are the base cases. Now, if we're going to consider some other examples, first, like numerically, we have what is alpha sub 2 of 1. That means we're in this state with t equals 2. And we're in t equals 2, and we're on the very first state, which is the blanks. The only way we could have gotten there is if we did 2 blanks. We outputted blanks twice. So like the states that we've gone through is the blank state and then the blank state again. So does this example make sense? Okay, next one.
Yes, basically, I guess just you went from here to here.
Why is that the only probability?
Because
It's just how we defined alpha.
yeah, so like if we've gone through 2 time steps, but we're still only on the very first state, which was a blank state, then that means like the previous step must also have been the blank state because there's nothing before it. So we must have outputted blank at both times. So it can't be like A blank because we've never gone through A. And then so for this case, oh wait, no, this was the case we've done this time. Wait, what was it? Okay. And so for this alpha sub 2, that means at time step number 2, we ended on state number 2. What we were in state, like in time step number 1 doesn't matter. We're going to sum over all the different ones that could have been. So like in one case, we started directly on A, and then we outputted A twice. And so the first path that satisfied this criteria was 2 A's. And the second path would be if we outputted a blank first time step, and then we moved on to state A at the second time step. And so in this case, we have 2 different paths to sum over to calculate alpha sub 2 of 2. It's a lot of 2's. Okay. Yeah, and then here's alpha sub 2 of 3. That means we have to have ended on the state with the second blank. And at this point, that means the previous time step must have been the A, because if we were in the blank in time step number 1, the first blank state, and then we jumped over to the second blank state at time step number 2, then we would have skipped the A in the middle, which is not allowed in like our list of transition rules that we've set out for this system. And so the previous step, we must have been on the A. And so the only path that satisfies this is A and underscore. I guess that's a little confusing. Anyone have questions? Is that a question? Okay. And so here's we're going to skip directly to time step equals 4. It's going to be a running example for the rest of the slides. So in this case, we have, here's the list of all the different paths that end on the B state at time number 4. If you see like all the different ones I've listed, they have B as the last symbol. And if you look at them, they also satisfy the rule. Like they always go through the A at least once. They never skip through the A. And like we know that these paths can't actually end in the blank state because if it had a blank state, that means we've gotten to the third. If it has a blank symbol at the end, that means we've gotten to the third blank state, which is not allowed because we're still considering that we're only on the B state at this point in time for alpha sub 4 of 4, where B is the 4th symbol in the sequence. And does anyone have questions here? Yeah.
So the A, B, C, C with the underscores, that's our modified input with the blanks, right?
Yeah, that's the modified labeling. And like right now we're considering as if we're only stopping right here, to right before the B, and right at the B actually. So like we're going to be using these to help compute the ones where we're stopping later. Then for this one where we're ending at the third blank state, which we couldn't do last time, in that case we have these possible outputs. All of them end on the blank state because we're on the blank state, and all of them end on the blank symbol. And okay, this last one is if we're ending on the first C state in the sequence, then these are the different paths. Again, like we can't end in the blank symbol, and we have the C's at the end of all of these. And for each of these paths, they make sense. And then we have all of these. If we're considering the next time step, suddenly we explode to like 21 different paths. If you think about it in like real examples, if t equals to like 20, then you're suddenly in trouble. Could be a very exponentially huge number of different paths to compute that, like by enumeration. So is there an easy way to find the probabilities of these paths? If you've been counting the numbers previously, you may have noticed that 10 plus 5 plus 6 is equal to 21. So there's actually a relationship between alpha of 5 of 6 and all the previous 3 numbers that we computed. Okay, does anyone wager a guess for what happened? Yeah?
So how the colors or the probability influence the result?
Influence the result of what?
They're just going to influence the result of the sum.
Yeah, so like we're summing the probabilities of all the paths. Where we're enumerating through, we're kind of like accounting for all the paths, but we're not using the probabilities to choose the paths.
So at the end, to get the probability of a path, you're going to do a product.
So the possible
Of the
state
biggest possible
has no
state.
influence on the probability.
How does
So
the
the probability have no influence on
the probabilities are helping us like, we're using the probabilities to compute the value of alpha, but we're not using them to like go through the paths.
Yeah, so they're not part of this algorithm.
Like,
So if we
We're
get
trying
rid
to
of the colors,
we're trying to compute a quantity based on those values, but we're not using them to actually select the path that we're considering.
yeah, so like I guess maybe programming analogy, you have a deterministic program which reads from memory but doesn't like branch based on what the value of memory was.
can you go back to the last slide? So can you explain how the probability influence the 21 passes?
It did not.
So like, no matter what probabilities that we had in the table, these 21 paths will still be the 21 paths valid for this state. Yeah. Yeah, but then like to compute the value, you still have to find the probabilities of each of these paths. This is where the probability is used, but it's not used to figure out what paths are available.
What you're saying is imagine writing a function to read from memory and sum up a bunch of numbers in an array. You're saying just get rid of all the numbers.
Oh, my question is that that picture do not influence the 21 passes, right?
No.
Yeah, it doesn't affect. Okay, no, it doesn't
It's not
affect.
changing your control flow with the values of those.
Okay.
Well, in the general sense it does, because you decided that some of the transitions are illegal, so
But that's not based on their.
So like the ones that I mentioned is like, we haven't gone through that state where like we're on a state and we can't skip through the blank because the next one's the same. But we do still have to go through these in order, and we're allowed to skip some of them. And so that's why all of the paths that we considered here, they have an A, they have a B, they have a C. They may or may not have blanks. Does that make sense?
Yeah, so I guess like I guess like each individual probability of the symbol is like it doesn't reflect necessarily like whether you're going to take an illegal path. Like if you're in t minus 1, doesn't change the probability of the next symbol once we actually like if it's illegal, it's not necessarily like compensating. It's not as if it's like a process where there's a zero probability of transition.
So like even if sometimes like some of these paths have zero probability, we're still going to be taking them into account.
So how to
How
get
to-
this 21 passes?
So how to like figure out what these 21 paths were?
Yeah.
In this case, I just like manually went through and figured out which ones were possible. In principle, you could make an algorithm, but even still, it wouldn't be very practical because soon there will be like an exponential number of paths.
So how to determine this one is match this requirement, that one is not?
Um,
I mean, there will be more than one passes for this.
no, I basically like systematically gone through all the possibilities to make sure that there were only these 21. Anything else is not like is going to violate something. It's either going to miss one of the symbols or it's going to like skip something.
I think the thing is like even though here you enumerate the paths,
Yeah.
this algorithm is exploiting this like subpath property such that like we're trying to compute the sum of the probabilities of the paths, and we can do that without explicitly enumerating them. Even though in the example, Jerry's gone through and
Yeah, so like in the previous ones, we had 10 paths, 5 paths, and 6 paths. And so like there's a recursive way to figure out the number or the set of different paths to get there. And similarly, we can use this kind of recursive relationship to find the sum of the probabilities.
You mentioned that there are some paths will violate
Yeah.
the rules. So what is the rule?
Basically, we have to go through these states in order, so we can't go we can't start at the B and then go back to A. And also, we're allowed to skip the blank, but only if the two symbols on either side are different, which hasn't happened yet. So the two symbols on either side are always different so far, so we haven't had to worry about that yet. And so the end result would be, in all the different ways we transition through the states, we'll be getting through A at least once, we'll getting through B at least once, we'll be getting to C at least once. And if we go on to the end, then we'll definitely have to go through the second C at least once.
How you hard coding those rules in your procedure?
It's going to show up in how we write the recursive relationship, which is going to show up in the next slide.
Yeah, it seems like A follows B and C, and the blank can be anywhere.
In this case, the blank can pretty much be anywhere except the end, because we haven't gotten to the state where we're outputting blank at the end.
Do you have a rule for limiting the number of times you can repeat a character?
No, you can repeat it.
You can get kind of stuck in C forever.
The only limitation is that you have to eventually go through all the other symbols at some point. Otherwise, it's an invalid path. So if you say something like cat, it will be staying in the A state for a very, very long time, but it's still valid as long as it has a C and a T in the end. C in the beginning and T in the end. Does that make sense?
Yeah, it does.
Okay. And so here's where we talk about this recurrent relationship. So to get to this point where we're at time 5 and we're at the first C state, there's only several different ways we could have gotten there. So possibility number 1 was we were at the B state at time 4, and we skipped over the blank to get into the C state at time 5. And possibility number 2 is that we were at the blank state, and we've moved normally to state C. And the last possibility is that we were at state C at time 4, and we stayed there for time 5. And so in all of these 3 different cases, you would get a valid path that the ends that gets to time 5 and is on the state number 4, which is the first C state. And so in all of these cases, we're going to output another C at the end. So the path that we consider each of the paths from these 3 cases, and for each one, we multiply again by the probability of outputting a C at time 5. So in this case, we've notated that with probability sub 5 of C, multiplied by the sum of all the 3 different alphas. And so as you can see now, 5 turns to 4, and so therefore this whole thing is going to eventually reach the base case where it's t equals 1. This is a recursive algorithm that will terminate. It will actually compute the values that you want. And it's also, you can also use it for dynamic programming, because you could in principle think that alpha sub 5 of some different number will be using alpha sub 4 a lot. And you don't want to recompute those. So by computing a table of the necessary probabilities, you can compute this very efficiently. And so it's clear. We'll be showing an algorithm very soon, like the pseudocode.
Can I point out the P5C which block?
Oh, you want to know which one it is in the matrix?
Yeah.
It's the one over here. Yeah, there's 2 of them with the same color, but it's that one. Make sense? Okay.
It's C, right?
What?
Because it's C.
Yeah. So A is on the top, B is the second row, C is the third row, blank is the last one.
Can we think this is kind of reduce the parameter space to search, but we do not give any rules to how to search?
So we gave some parameters rules to figure out what to search, and then we
Reduce the parameter space, reduce the target space.
at this point, At this point, we didn't make any correctness changes, so we're not reducing the space of things to search. We're just computing it in by taking advantage of kind of redundancy.
You in the first you mentioned probable paths will be very large, but after you doing some kind of rules, it will reduce to 21.
Basically, what I said is that even the 21 is a very big number. If you go into alpha sub 6 or 7 or 8, it'll suddenly turn into the hundreds and thousands, even with all the rules.
But his example was he only needed to calculate
Only.
the values for what, 5, 6.
So like we're reducing 21 into basically 3, if you want to think of it like that. Where 3 is like values that we computed earlier. Basically, like we're using 3 previous values that we computed earlier to compute the next one. So like there's this kind of sequential way of going through alpha sub 1 of everything and alpha sub 2 of everything. Yeah, it's dynamic programming. You do something very similar for hidden Markov processes.
Yeah, if you just see the forward, backward out of each of these.
Yeah. I actually learned this before hidden Markov models. Oh, dang. Okay. And so like this is just a graph showing like what's happening. So we're at these 3 are the 3 different possibilities of where we were at time 4 that could like have validly led us to time 5 being at state C. Like if for any other case, for instance, if we're at the second underscroll state at time 4, then we can't go to the first C state at time 5 because you'll have to skip over the B or something. So these are the only 3 possibilities for where we were previously. Okay, and here is kind of pseudocode for what's happening. This is just kind of some, this is just a little bit of a checking to make sure that whether or not we can skip. And in these cases, we have a different like recursive relationship. And in the first case, if we've shown the case where we entered into this clause of the if statement where we were allowed to skip because.
To reduce confusion, I think that A of T of S got bumped up to the comment. Imagine
Yeah,
the A of T of S on the next line below the comment.
Yeah, it didn't fit in the line apparently. And then like the other stuff is some bookkeeping to define what we mean when like we have alpha t minus 1, but t is already 1 or something. Or if we have s minus 2 and s minus 2 turns negative or something. The first few lines are just bookkeeping. And then we have the base cases. And we can compute this stuff. If you're actually coding this, you'll have to actually create like a table to make sure you're not recomputing some of these values. But this is like in pseudocode what's happening.
Is this the Markov decision with steps 2, right?
It's a recursive relationship where we only step backward by up to 2, yeah.
But in
Yeah.
for you already take care of 1, that's 1, yeah, right?
We already took care of what?
That's equals 1.
Def equals 1 for the previous one is, we have def equals 1 because we have t minus 1 in all of these cases. The s minus, because like, the reason, so like s could conceivably never change throughout the recursion, but t definitely goes smaller.
So why is t minus 1, t s is related to 3, not 3, 2 state minus 2 and state minus 1?
So like in the state minus 2 version, it means we've skipped through state minus 1 to end up at state. So state minus 1 being the blank state, if state minus 1 is the blank state, then we could do something like that. And then for this case, that means either we're doing the blank state, so we couldn't skip through the previous one, or we're at a non-blank state, but then we couldn't skip through the previous blank state. So like the paper combines these two into a single statement saying, well, if the labels at the state is not the same as the labels of the previous, of the state minus 2.
Oh, so state minus 1 is blank, it can be state, right?
Usually, unless it's the same symbol on both sides. But yeah, you can think of it as almost always it can be skipped. Okay, that makes sense. All right, so now basically, finally, we can compute the loss, CTC loss, which is we use like the alpha with the biggest possible values. So we have to get to the end of the sequence. So we have alpha sub n of alpha sub n, and then we have to either reach the final state, which was the blank state at the end, or we could have reached the state right before that, which is like the last non-blank symbol. Both are like valid in terms of like they collapse into the ones you want. So you just sum over those two different, you sum over the paths for both cases, and you do a negative log of that to find the CTC loss. Okay, does that make sense? Next one, I guess. And then there's a small thing, a little issue to talk about for the derivative, which is like how will you compute the derivative of the loss with respect to each of the probabilities? Because once you have that derivative, you can backpropagate that and then tune the rest of your network, since your network created the probabilities. So like how are we going to compute something like this? So we know that the CTC loss looks like it's made out of some stuff related to alpha. And so we might say, how do we find the derivatives of alpha with respect to the probabilities? And this is the case I've shown here is like a very easy to compute case for alpha, which is if we want to find the derivative of alpha sub t of s with respect to probability sub t of whatever label that was at, let's say, s, and then we can know that the way alpha sub t of s is computed, it's a probability of that symbol appearing at that time times some kind of constant, that constant being like the sum of some other alphas. But no matter like what that constant is, being a sum of a lot of different alphas, it's still constant with respect to the probability of the label at that time. And so like, does anyone?
I think you missed the right practice.
Oh, yeah, a little typo. Because we were moving everything from Google Docs to a LaTeX, so we may have messed up at some point.
We'll re-upload this. There were some typos earlier too.
Yeah.
We'll re-upload everything.
Okay. But then anyways, like to compute the derivative, it is just that constant. And you know that that constant is just the alpha divided by the probability at that point. So it's actually very easy to compute the derivative for that case. Can we do something similar for CTC? And so this is the point where we bring up beta. So beta is very similar to alpha. The only difference is that instead of making paths starting from t equals 1 up to like t equals up to time t, we're going backwards. We're starting at time n, capital N, and we're going backwards up to time t. And then similarly, we're going backwards through the states with the same rules where you can't skip through blanks. You can skip through blanks unless the same symbol is on either side, so on. So it's a very similar computation. It's just everything is backwards. And so basically, it's the pseudocode for beta. You can look through this. It's almost exactly the same as the one for alpha. And a little typo again. This one should be beta.
Oh, yeah, this should be beta.
Okay. And then next one. So there are some properties of beta that we can use to help compute the CTC loss in a different way. So in this line, we're saying we're taking the product of the alpha and betas at the same t and s, and we're dividing by the probability over there. Basically, what's happening is we're considering all the paths that get to time t and end on some certain state, and then we're considering all paths that start at that state at time and go on to the end, which is the first one being alpha, the second one being beta. You have to multiply the two, and we also have to do a little like division to keep track of the bookkeeping, which is the fact that we've like overlapped at the one place where they intersect. And otherwise, we have to sum through all the different states that we could have gotten to at time t, and we get a formula for the CTC loss. So that formula should hold for any value of t, and it's an alternative way of calculating it that helps us find the derivative. And so another thing about beta is that it also has the property that like the beta t of s is just probability t of the label at state s times some kind of constant, which is the sum of several other betas, but it doesn't matter. We can find the derivative to be equal to that constant, which is just beta divided by the probability. Okay, and then finally we can do a little bit of calculus to figure out that the derivative of the CTC loss can be computed like this. Basically like some terms of the sum, like a fraction of the terms of the sum will actually be turned into 0, and then the product of the two divided by the probability is product of two constants times the probability. So we differentiate that, we just get the product of the two constants, which is the alpha divided by p times the beta divided by the p. And then we also have to do a thing because we have negative log on the outside. But in the end, we get something like this. Is anyone clear? Don't need to know exactly how this is done immediately, but okay. And then just a little point about inference, which is so far this is all for training. We compute the losses, we compute the derivative of the losses, but how can we like figure out, like once we have the network output at the end with all the probabilities, what are we going to say is like what we're going to label our test data with? So in one case, we could have just used the most probable like labeling, the most probable path or something. And that could work. It's not completely bad, but it's like a heuristic. It's like a greedy approach. So if you think about it, like if you find the one most likely path, it's not necessarily going to collapse into the most likely like output labeling, because maybe the most likely output labeling contains the sum of many good paths, just not the most likely one. And the most likely the output labeling that contains the most likely path might contain some other very bad paths. And so like it's still possible that the most likely path is not the most likely labeling. So we could use there's some heuristics about it. Has anyone heard of what a beam search is? Okay, so like a beam search is basically a heuristic way where instead of considering the one most likely path, we consider essentially the top k most likely paths. And then in that case, like as we go through it, we can update what our like top k most likely paths are. And so in the end, we are more likely to find the like actual most likely labeling. And then we can also use dynamic programming to find the actual answer. It's kind of like inference for hidden Markov models. But then like for the most part, for testing purposes, you can use the most likely path. It's not a completely bad approach. And then just some more practical concerns. These two, alpha and beta, are both going to be very close to 0 because it's like a product of many, many probabilities. So what we do is we use the logarithm of them. And then we replace multiplication with addition. We replace addition with this function called log sum exponent, which is basically addition in log space. And second one is just a personal thing that I found was that it could still take a lot of time to compute if you write it like in Python without optimization. And so you can use a library or use a different language or use vectorization. Okay. And see, I think this is the last slide, right?
Yes, it's the last. Yeah.
Okay, it's basically the last slide. So this thing is what we talked about, which is that this version of CTC is the one that shows up in the paper, but there's actually, CTC itself is a family of loss functions. And so we could make it follow many different rules, not just the one we've mentioned with like skipping the blanks and whatnot. And so you could have no blanks if you want. We just have a different recursive relationship. You can even follow certain like state machines. For instance, in homework 1, where we had 3 different parts for each phoneme. And you have to go through part 1 of the phoneme and then the part 2 and then the part 3 for it to actually count. We can make a recursive relationship that enforces this. And then the only difference is that we have to use a different recurrence. Okay. Yeah. Does anyone have questions at this point? We have a little notebook afterward. Okay. Slides are available on Piazza, right?
Yeah, they're on Piazza. They'll be up on the course website.
Okay.
And once they're up on the course website, they'll be corrected.
Yeah.
At least. So if you guys noticed anything and didn't quite
Okay.
have much, or just
Do you want to talk about the?
Sure.
Okay.
Check the notebook.
Yeah.
All right. So in the 9 minutes that we have remaining, I'll pull it up here. I can get
Which
it.
one's escape?
Oh, here, I guess go over. This is it now.
Okay.
Where did we have it?
Oh, it's in the terminal window, isn't
Here we go.
it? Okay.
All right. So this isn't CTC, but last week during rest, make it bigger. Now, good. Okay. So last week when we worked with RNNs during recitation, we had an architecture where at each time step we outputted single values. But we're going to look at an example of a recurrent network that outputs a probability distribution over possible values. So this is what's been you'll see it called a char RNN, where so in this case we're going over the corpus of all of Shakespeare's works, and basically given a character, predict the next. So this should be up in the tutorials repo, and you can download it. They're just it's very similar to the recitation from last week, but there's really one important point that I want to make, and that is you can see here we have 3 LSTMs stacked, and when we output a distribution, and the way that we sample from it is we do this thing where we actually add noise from the Gumbel distribution and take the argmax. This ends up being analogous to, say, actually generating a categorical distribution and then just sampling from that. So we do that here. But one important thing is that for the next state, once we actually sample, so if you can imagine for the word King Richard in Shakespeare, if we're at the if we see the letter R, and then we sample, and then we get the next character I, we need to re-embed it, and then pass it into the next time step.
So like the workflow is start with a character, pass it through 3 RNNs to get a probability distribution of the next character, add like noise to it, and then take the most likely, take the argmax most likely character from that, and then regenerate like a one-hot input to pass into the next step.
Mm-hmm. So then, one interesting thing is that if you don't sample randomly and it's deterministic,
It'll give you the same.
so if we start with a blank, it's it just turns out that it's more probable that it'll always be a blank.
In this case, I think it's an issue of seeding. But
Is it seeding?
yeah.
Ben,
So, like,
did
we
you
start
determine
with-
that seeding?
The next one is deterministic, but we choose different seeds. But like in either case with deterministic, we get a lot of repeated behaviors.
Yeah, so an interesting thing to point out is that if we seed it with King Richard, you could actually see that it's King Henry is the most probable word that could be generated. But because we're seeding, as soon as the network sees a blank after King, and then it outputs an H for Henry, but then as soon as it sees I, then the next most probable word becomes Richard. So that's why it's Ing Hitchard here. And then after that, it gets a little neurotic. It's sort of like out of The Shining or something.
God, the man and they are a state of the world. The man and they are a state of the world.
Ben thought it could be a good pop song. And then then we have the copyright notice. All right.
So I think this is word level or the type level?
This is the character level.
Yeah.
And now with the Gumbel noise,
Get more interesting.
we get more interesting. So you guys can download this and play around with it. It'll be some good sample code, and you can also generate some fun stuff like this too.
The anomalies didn't show up in the place.
But I mean, as you can see, what's really interesting is that it does learn this long-term structure. So even here, it realizes that you need to give your character name before you start speaking.
If you look into like this web article about the unreasonable effectiveness of RNNs, you would get some really impressive outputs as well.
Yeah.
More impressive than this.
I think in lecture, the professor showed the Linux source code character generation. But I've done it with like, you can use the TensorFlow source code. That's a little meta. Yeah.
Yeah, so like just a reiteration. So like the obvious way of how to make an RNN would be to
given the input probabilities, it outputs the next output probabilities and feed that back in. That's like how we've dealt with RNNs forever. The output goes directly back in. In this case, it's just different because we have to actually like commit to one of the argmax of the probability distribution every time, and maybe add noise in the middle. So like that way, you would have to do it one character at a time instead of using the built-in function in PyTorch that lets you do the entire sequence at once.
Yeah, so our sequence length for each one of these is just 1. And then we just keep, but then we take the previous hidden state and store it, and then feed it back in at the next step.
Mm-hmm. Okay.
Okay.
We actually managed to finish earlier.
Yeah.
Wait, Ben, is there anything else we should mention for this? Wait, Ben.
Yeah, the main thing was that without noise, like you get these like weird pathologies.
Yeah, like in the first case we got like 2 Galvin spaces, and in this case we get the one phrase being repeated many times. So that's like, if you let the recurrent network basically do like feed itself back in over and over, it'll eventually find something similar to like a fixed point, and it'll do that over again and again. Yeah.
What's the relationship between CTC and sequential modeling and RNN?
So like CTC is used is like a loss function that's usually used when the model is in RNN, and we have like these streaming outputs. This is a
So like here we have a fixed label at every output step, right?
This is a generative example though, so it's like
But
a different architecture.
while training it though, right?
So CTC is not used in this example.
Oh no, but I'm just saying the difference is that in this example, given a character, we have a label for the next character. In CTC, if you have 1,000 time steps, and say that whatever, if that's a speech recording, and actually all you're saying is cat, what's your loss on that, based on the right?
With generative, we can at least say like you're supposed to output this symbol at this time. Problems with it, but at least it's the thing you could do. With like the streaming many to many architecture, you'd have you don't have a direct mapping from your output labeling to the input, to the inputs. Yeah.
So is CTC used for unsupervised learning?
It's not quite unsupervised, but it's like not quite as supervised as like one output, one input, one label. Instead, it's like many inputs, fewer labels.
With a blank.
And you can use blanks to like calculate. You can use blanks to basically create like a mapping from a really long output to a shorter label.
And there are places where you don't actually need blanks, right? Because I mean, blanks like implicit that something is remaining constant and it hasn't changed. So actually, blank, in fact, for different characters, for different labels that you start at, if you're at A and then go blank, or B and go blank, those could actually be different labels on their own. That's just a setup that the original CTC paper used. Why we describe it as a family of loss functions, and it shouldn't be thought of as like the one and only way to go about doing it.
Can I understand this CTC as many-to-many, but with many outputs, which the output is not like all available. Some outputs, some time steps output may be not available, right?
There are many possible.
Similar like to that, except because some of them are not available, the others can move around and you don't know where they actually are.
Okay, move around, yeah. So how to construct the loss function for this 90-to-90 RNN with CTC?
CTC is the loss function that we're
Yeah,
using.
So in the slides we went through, and you can go see the derivative, calculation of the derivative and everything.
Will this CTC model cover the after course?
I think Professor Fixter will be talking about sequence to sequence for a little bit as well.
So that's going to be the end state.
Yeah.
Mm-hmm. All right. Thank you, guys.